Today we're learning about Newton's first law of motion. So you remember when we learned about forces that we said that the unit for force is the Newton, named after Sir Isaac Newton because of all of his wonderful contributions to our understanding of forces in motion. Well, we're about to see some of his contributions. The very first one of them is his first law of motion. Today, the goal is that you will be able to explain relationships between an object's motion and the net force acting on that object, that you will be able to calculate net force on an object, and that you will be able to determine if an object is in equilibrium or not. So those are our objectives. Newton's first law of motion, there's lots of different ways of phrasing it. This is the version from your book, and it says, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity, that is to say, it is continuing at a constant speed and in a straight line, so it's not speeding up, slowing down, or changing direction, unless the object experiences a net external force. Unless, okay? If the object experiences a net external force, then we should see a change in its motion or state of rest. A common misconception that people have, and this is because of the way the world appears to work if we're not studying it carefully and closely, is that in order for an object to not have any forces acting on it, that object has to be at rest. Okay? This misconception arises from the fact that here on Earth, it appears to be true that the only objects that are not experiencing forces are at rest. And that's because of this nasty little thing called friction that is nearly impossible to do away with here on Earth where we have gravity and surfaces have to touch. Okay? Here on Earth, if you push a block, even on an ice rink, which is as close to frictionless as we can get here on Earth, that block will eventually stop. Because as minimal as the friction is, there's still friction there, and so it is going to slow it down. However, if you were to take an object and put it in a frictionless environment, say a complete vacuum with no gravity, okay, and you were to push that object and start it in motion, that object would continue in motion forever, indefinitely, until another force were to act on it. Say, a wall, or friction, or gravity pulling it down to Earth. Okay? So, it is possible for an object to be moving and have no forces acting on it. It just doesn't happen here on Earth where we visually see objects, because there's almost always some force acting on the object almost immediately, and so we are never able to see an object with no forces acting on it.
So like in space, when they're like in the space shuttles and you see the thing moving, like the thing's floating, they'll continuously do that until they hit the walls or the space.
Right, and even on the space shuttle, it's better, but it's not perfect, because while they do not have to touch an object to move, right, so a ball can float through the air, it does still experience air resistance, so it would eventually stop even if it didn't hit a wall. But if you could put it in the vacuum of space where there's no atmosphere, then it would move continuously. Unless, of course, it ran into space dust and particles and things that happen to be also floating out in space. So,
but in a perfect idea.
In a perfect world, in a physicist's world where we can ignore things like friction and air resistance, it would continue indefinitely until a force acted on it. The reason for this is because of a property of matter called inertia. If you've ever watched the opening to Bill Nye, you've heard inertia is a property of matter. Okay? Inertia is the tendency of an object not to accelerate Or, phrased another way, inertia is the tendency of an object to resist changes in its motion. Go back. Now let's talk about net force. Okay. Think about a car that's moving at a constant speed. Okay. What are some forces acting on a car that's moving at a constant speed? Its speed is not increasing or decreasing.
Friction with the road.
Friction with the road, definitely.
With the air.
Friction with the air, too, probably. Yep, air resistance.
Gravity.
Gravity pulling down on the car. Okay.
Ground on car.
Ground pushing up on the car. Okay. And then likely the engine is exerting some kind of force to propel the car forward, right? Okay, so in order for that car to stay at a constant speed, it needs a net external force of 0 in order to fit Newton's first law of motion. Okay? But we know there are tons of forces that we just listed that are acting on that car, right? We have the force of the engine. We have the backward force of friction on the tires. We have the downward force of gravity, the upward force of the road. So how can this car be experiencing 0 when it has all of these forces acting on it?
Because it equals out.
Yes, because it equals out. So the difference is being able to tell the difference between net force on the car and external force on the car. So the difference between external force and a net external force is very important here. An external force is just a single force acting on an object. Obviously, the external forces on this car are not equal to 0, right? They're forces, so they're acting in a direction and with a magnitude. However, the net force is a vector sum of all the forces acting on an object, such that if you have your net force, it would produce the same motion in your object as the combination of all of the other forces. Let's try out doing a net force. Okay, so your book provides this excellent example where we have 3 forces. The magnitude of these forces is actually equivalent to the magnitude of your bite force, so the force you're able to exert with your jaw, which is 4.33 times 10 to the 3rd newtons of force. Okay, so I want you to try this because it's just vector addition. We have done vector addition before, okay? You have one vector, like if we set up our axis, right, so that it's like this, right? You have one vector that's on the x-axis, one vector that's on the y-axis, and then one vector where you will have to resolve into its components. And then you can add them just like you would add any other set of vectors. Okay, so give it a shot, and then we'll come back and do it together. Okay, let's try running this. Let me clear my stuff. Okay, so in order to sum these, we need a total x and a total y, and then we can use Pythagorean theorem to find the resultant. So, fortunately for us, we only have to resolve one of these into its x and y components because the other 2 are on the x and the y axis. So our force of x will equal F2 plus F3x, and our force in the y direction will equal F1 plus F3y. Okay? So in order to solve for F3x, we need to do cosine of negative 60 times F3, which is that 4.33 times 10 to the 3rd, which should come out to 2.16 times 10 to the 3rd newtons. And in order to solve for F3y, then we're going to do sine of negative 60.0 times 4.33 6.33 times 10 to the third, which should come out to roughly negative 3.75 times 10 to the third newtons. So the reason they made 60 degrees negative is to indicate that it's in the quadrant that's under the positive x-axis, so that just our y value would come out negative. Okay? All right, now we can take these numbers and move them up here and add them together. So if I wipe my screen, we should come up with a total force in the x direction of 6.49 times 10 to the third newtons, and a total force in the y direction of negative 8.08 times 10 to the third newtons, roughly. Okay, you may have rounded slightly differently than I or the book did. Okay. And then we can use Pythagorean theorem, so we just do the force resultant, okay, is going to be equal to the square root of this number here, which I'm just going to call fx squared. We're trying to find the resultant. We had to add them together. We had to add the x values and the y values together to get our total x and total y, which we did. And then now we take our total x and total y and use them to find the resultant using Pythagorean theorem. So then fy, which is this number here, squared. And you should come up with a resultant of 1.036 times 10 to the fourth newtons. Okay. And then if we want to find the angle relative to the x-axis, then the opposite will be the y. So if we're going to use the theta is equal to tan negative 1 opposite over adjacent, whatever our final y value was over our final x should give us our angle, which should come out to roughly negative 51.20, which just means 51.2 degrees under the x-axis, the positive x-axis. Okay? All right. I believe that was our bell. We have just a few notes to finish, but we'll finish those up tomorrow.